all these things are, I mean, imaginary, and so when we create the concept, so concept is already in place. We're trying to just narrate a story that how we can explain or interpret the given electrostatic phenomena using the concept of EF. So the electric field lines is just like we are reinterpreting using this concept. It's clear.
Yes, sir.
Okay. So the next property is action person. So now we will try to understand the behavior of electric fields in case of conductor. And this is going to be very important concept. The first thing is, what do you mean by conductor?
So your voice is a bit low.
Am I audible now? Is it better?
Yes, sir. Yes.
So the question is, what do you mean by conductor?
Mm, where the electrons are free to move.
Correct. So conductor represents a medium in which we have free and mobile charge carrier, which may be electron or ions. So in case of electrolytic solution, the free charge carriers need not to be just electrons, it can be some other different ions. In case of metallic conductors, the only charge carrier that we can have is ions. And in case of semiconductor, we have two types of charge carriers, which we call electrons and holes. And in case of insulator, we don't have any charge carrier. So a medium with a property to generate the free charge carrier by some process, such medium is called conductor. And most of the metal falls under that category. So the way to define conductor is simple. Any medium with inexhaustible supply of free charge carrier any medium with inexhaustible supply of free charge carrier is called conductor. So now we need to know the property of conductor. So the property that we can say is every conductor always maintains charge neutrality within its bulk. So if we talk about conductor, no matter whether we give charge or not, the conductor will have its own positive and own negative charge, and those positive and negative will distribute homogeneously. So the homogeneous distribution of the charge will try to maintain the electrical neutrality. Okay. So that is the first property. So a conductor will maintain the electrical neutrality within its bulk. Bulk means the volume part. And therefore, the second most interesting property, any excess charge given to conductor, any excess charge given to conductor will reside only on its surface. Therefore, therefore, any charged conducting body will behave as hollow conductor since charge only occupies its surface. So when I say conductor, it means conductor, let's say drop. So let's say this is a random conductor. So the bulk will try to maintain the electrical neutrality. Even if you give some charge to the conductor, it will keep on repelling the charge till it becomes part of surface. So the simple rule is, if you supply charge, so the bulk will never be the host for the charge, only the surface will host the charge. So all the guests will be part of surface.
Okay, sir.
So their territory will be only the surface. So it is as good as like a hollow connector, because the charge is not becoming part of the bulk. So bulk is electrically neutral.
Okay, sir.
So bulk is and not just neutral. Bulk will have the net field equals to 0. It means if we have some field which we apply, and if we have some field that we create by virtue of charge, the resultant field within the bulk of conductor cannot exist, and it will be always 0. And that is the property of conductor. So no matter what you do, the bulk will never ever will let the electric field to develop. So it will do something, And the good thing about the conductor is that it will allow the charge to redistribute itself over the surface. So charge can move across the layer of surface, and the movement will always happen in such a way to make sure that the net field is zero within the conductor. So that's the first criteria. The net field is always zero within the conductor. Understood? Hello?
Sir, by net field, I don't understand. So,
Yeah, net field means like the field which is either developed by the charge or the field which is maybe already present in the space before bringing this charge. So, for example, so if you remember the induction process, which is a really nice property of every conductor.
yes, sir.
Let's say if we have a electric field in space, let's throw something like this. So let's say the electric field is something like this. So this is the applied electric field. Let's call it E. And the next is you create a conductor, some random shape. And not only this, you have a conductor now. And this is some random conductor. So as we know that every conductor will have free electrons, but the free electron of a conductor will be like the Thomson plum pudding model. So you can imagine the charge as some plus and some minus nearby. So when I say electrical neutrality, it means we have the homogeneous concentration of plus and minus. That's the general property of every conductor. Like now, among the plus and minus, you can always imagine or remember that the plus are fixed quantity. You cannot move the plus, but the minus is representing the mobile electron which can move. So the moment you apply the electric field, what will happen? This
The
electric
electrons will
field,
move opposite.
it will try to push the plus towards right, and it will try to pull the negative towards left, right?
Yes, sir.
So all the negative charge will start accumulating on this side. As a result, the extreme surface on the other side will acquire the positive charge. But in the bulk, the neutrality is still maintained. So only the outermost layer will move towards this side, okay, on the left hand side, and the eventually the polarity which will remain is the minus on the left surface and plus on the right surface. So the whole purpose of this process called polarization, the whole purpose of this polarization is to make the net field zero. So how they will make the net field zero? So you can see the plus on the left and minus on the right will again create its own field like this. You see that?
Yes, sir.
Something like this. So one field is something which you apply, and other field is something that is called induced field. So what we have here? We have the induced field on the left side due to the charge accumulation. If you look carefully, the conductor is able to create its own electric field, right?
Yes, sir.
So the induced field. but we already have something existing everywhere, and that is the applied, the E. So the conductor will make sure that the net field is zero. It means the induction process will create the electric field exactly same as the applied, because the net within the bulk will be zero. So the property of induced field is it only exists within the volume of conductor, and induced field will always try to nullify the external field that we apply, and the net field will be again zero only. Understood?
Yes, sir.
Now the question is how to represent the lines of force in such case. So the simple rule is conductor will never ever allow the electric field to enter its bulk or the volume. The rule is simple. The property of conductor is to terminate all the field lines on its surface and re-emanate the lines from the surface itself. The bulk, because it represents the zero electric field, and the graphical way to represent the zero electric field is do not draw any field lines. That's the whole idea.
Yes, sir.
So the way it happens is, if we have a conductor, and let's say here I applied the electric field, instead I will assume some hypothetical charge here. So generally conductor is neutral, but in the presence of the field of the charge, so imagine the charge doesn't know about the conductor. So the way charge would have created the field will be like this only. So charge alone will create the field like this,
Yes, sir.
radially outward in all directions.
Yes, sir.
Now this is the assumption. I'm assuming that okay, charge is not aware of the conductor. So anyway, when I will create the field lines, I don't know what is kept ahead, right? I have no idea. What I know is only that we have a charge and it can create field like this. So what happens again? Because the field will try to enter the volume of conductor, the electron will be attracted by the field, and therefore all the electron will try to come this side. So electron will travel this way, and a flux will create this way. Now, as a result of the charge motion, or you can say the what we call polarization, a field will also develop in the reverse direction, and this will be called E induced. Okay? The white is the applied field. So imagine that the E induced is weaker than E applied. Like let's say I'm assuming the field of the charge is dominant over the field that the conductor is inducing within the volume. So as long as the field is unequal, what will happen? If E is more than the E induced, what will happen? The electron will keep on moving towards left.
Yes, sir.
So eventually the more charge will accumulate on this side. So with time the induced field will become stronger or weaker.
The induced field will become stronger.
So there must be some time at which they will be cancelling each other.
Yes, sir.
So after some time, when the field of the induction and the applied field are equal to each other numerically and opposite in direction, the electron will be there, but it will not be able to move, isn't it?
Yes, sir.
Because both the force due to the applied and the force will cancel out each other.
Yes, sir.
So now, because there is a time duration up to which this will occur, And eventually when both will become equal, then the net field will be how much? Zero.
Zero.
So the question is, how much time it takes to make this possible? So the answer is it only takes you 10 nanoseconds. So this entire phenomena only takes 10 to the power minus 8 seconds for the charge to develop, left to go there, right there, and do everything. And that is the reason we call the process as instantaneous process. So technically there is no time lag because 10 power minus 8 seconds is no time. And in that small duration, everything happened.
Okay, sir.
Now the whole idea of electric field lines is to represent the resultant field, not the individual field. So when I'm trying to draw the lines of force, I cannot draw the field of positive charge or the field of induced charge. So what we can represent is the net field. So these are graphical representation, and what you must remember is that the electric field lines only represent the resultant field in space, not the individual field. Do you realize what I'm saying?
Yes, sir. Sir,
So, yeah.
yes, sir.
Then,
So by resultant field, so that like in order to hold up the fact like two field lines cannot intersect.
yeah.
Okay, sir.
When I said the net field, it means every possible charge in space will have some electric field. So when you draw the electric field lines in a space, then you represent the resultant field due to every charge possible there.
Yes, sir.
So that is the meaning of say since Eiffel only represents the, the resultant field at every point of space. Therefore, space with no field must have no field lines. So space with net field equals to 0 must have or must not have any. Second thing is, which you should remember, which we can prove later on. Your conductors EFL will will terminate or emanate at right angle to the surface of conductor. So what does it mean? That if we have a any random shape conductor, if we have a random shape conductor, So let's say the charge question that we talk about. So electric field will, of course, it will have some induction here, and it will induce some plus charge here, right?
Yes.
So how to represent the electric field? The answer is simple. Whatever will start from here will terminate the surface at a right angle. So no matter how it goes, but it will terminate at the right angle. So this is very bad conductor surface. Very bad voltage. So the angle at which it will terminate. So see, you can see the plus is here. So the front surface will have exact minus, and therefore every lines of force which will emerge will eventually terminate. That's the whole idea. So graphically we represent this. Okay.
Sir, I don't understand like why right angle.
Yeah. So we'll come to that. Let me do some parts. So why right angle is, let's say if it is not at right angle, just imagine. Let's say the electric field is at some angle like this, theta. Then the electric field will have component along the tangent.
Yes, sir.
Now, if the electric field will have component along the tangent, then the surface charge will be at rest or will be in motion.
So it will be in motion.
Then how the charge equilibrium will be attained? So for charge equilibrium, they will move such that eventually they will cancel the tangential component.
Yes, sir.
They cannot keep on moving forever, no? So at some point they will try to cancel the effect of tangential electric field, and therefore the whole idea of charge distribution is to cancel the tangential field.
Yes, sir.
Understand?
Yes, sir.
So because the tangential component will cancel out, then which component we are left with?
So the normal component.
The normal component. So it means the electric field, the net field will be always perpendicular near the surface, right?
Yes, sir.
So that is the reason why we consider like this. Okay.
Yes, sir.
Now similarly, if it will terminate on the left side like this, it will emanate back from the right side by positive charge, but again at right angle. So emanation or termination will happen at right. So that is the property of connector. It always terminate and emanate. So the thing is, the rule of connector is it will like stop and restart with a gap. So the field lines cannot be present in the bulk, and therefore you can understand that the net field will be here. So what we are representing is zero field because I'm not drawing anything is equivalent of no field is there. No means no net field is there. And when I say the lines of force, it only represents the net field. So you are not looking at the individual field lines. So these field lines are the combined effect of the charge given and the induction process. And that is what we represent. Is this clear?
Yes, sir.
All right. So let's say we have some random shaped conductor. And there is a cavity present within the conductor. So this is the conductor, and this is the cavity. So if you bring any plus charge here outside, then the field lines will be beginning from here, terminate, and will again restart from the other side and will go forever. That's how the thing will be. But imagine situation like this. So what if I bring some charge here? I put a charge here. So the moment you put a charge within the cavity, the electric field lines will start from the plus charge. But again, as we said, the field lines cannot go through the bulb. All the electric field will terminate on the surface of cavity only. And to do so, it will attract many electrons from all sides. So the wall of cavity will be negatively charged, isn't it?
Yes.
And the field lines will terminate at right angle. Here it looks right angle. So it may be informed or non-informed depending on the charges. Spherically, cavity is spherical, charges at center, or charges kept randomly. So what you can realize that the moment you put the charge in the cavity, the field will start from the charge and will end at the cavity. That's it. Okay.
Yes.
Now, as a result of induction, if the minus will appear here, then plus will appear where?
So on the boundary of like the outer boundary.
Outer bound. Now, can you see electric between the negative of the induction and plus of the outer boundary? The answer is
Yes.
no.
Oh,
The net field is zero. No?
yes, yes.
So we cannot draw field lines like this. This is not possible. So again, the field lines will recreate from the plus to the outer world like this.
So since the electric field lines produced by that external charge is already terminates in the negative charges
Yeah,
that are like near the boundary,
correct.
there is no
The
need for
plus, yeah.
the positive charge to cancel out.
So plus is already permitting. So like they are like having the close bonding, but the plus on the outer surface is like a free charge. I mean that charge is not interacting at all with the other charge. So the plus of the outer boundary will actually meet the negative at infinity. Because if no one is there, we can always call. Let's say the plus will induce the minus at infinity. That's how we think about it. Why we say like this? Because eventually every field lines will terminate at infinity. So no matter where the field starts, at infinity, all electric field lines will terminate, isn't it? So we
Yes.
can always think the infinity as the negative charge boundary, which is not visible to us. So there are many concepts that you will come across in this cavity problem. So there is a concept of bound charge and free charge. So now the outer surface is surface bound. So outer charge is the surface bound, which means it will be part of the surface, but it will not leave the surface. The inner negative charge, which is the induction process, is actually bound to the plus charge. Now, what does it mean? The existence of the negative charge is due to the plus charge in the cavity. Understood? So they will ask you, can we remove the minus charge by any method? And the answer is no. Why? Because the birth of minus charge is not due to someone else, but it is due to the plus q charge which is kept in the cavity. So who can affect the minus charge? The answer is the plus in the cavity. So only way I can remove the minus charge is by removing the charge itself from the cavity. Understood? So what I'm saying is the cavity charge in the cavity. This is induction producing induced charge. So this minus is due to which charge? The cavity charge.
Yes, sir.
And you can see there's a direct connection between the plus and minus. So this is the lines of force, the green one.
Yes, sir.
So we say the charge is bound to the plus Q.
Yes, sir.
So the question is, can we remove this charge?
So remove this charge by,
Maybe grounding and all something, or by putting some charge there.
so since it's attracted to the plus Q charge, so we cannot influence it by using any other method, sir.
Correct. The negative induced charge cannot be changed, cannot be altered, because the reason why that charge came at that location is the plus in the cavity. So the creator of charge is the cavity charge. So the only one who can disrupt or alter that charge is the charge in the cavity.
So what if we place another charge inside that
Then,
cavity?
then together they will try to influence. So you are saying that okay, you want to put something else, no? Q and
So
let's say minus
yes, sir.
2 dash 2 dash. So if you put two charge, then the two charge will create a resultant field again, and the net induction will be depending on the two charge itself, the sum of the two charges. Okay.
So some more electrons will come to the
Yeah.
inner boundary surface.
If you bring more positive, then more electrons. But if you let's say bring some negative, then it will the net value. So let's say you bring plus 2Q and minus Q. The net is only plus Q. No?
Yes, sir.
If you bring plus 2Q and plus Q, then 3Q. So the
Sir,
net,
yeah.
let's say you are bringing some charge here, let's say minus. Okay.
Yes, sir.
Now, if you bring plus Q and minus Q, the field lines will be very complex, not like this. But whatever will be, that cannot be altered by any external intervention. That is the whole idea. Any charge distribution which generates on the inner surface of cavity, the cavity surface, can only be altered by these two charges. That is the only fact.
So like any influence that comes near to the outer boundary cannot influence these charges.
Correct.
Oh,
But
okay.
the outer charge can be influenced because that is not bound directly with the. So see, I have kind of pulled all the electrons near my cavity. So the outer will have deficiency. That deficiency I can fulfill. No?
Yes, sir.
So see, I have taken whatever I needed. So now outer surface will have some lack of charge, which we represent by plus charge. So that I can come and fulfill. That is possible. So the thing is, this is called the unbounded charge. So the outer charge is unbounded, so that can be influenced by various techniques. Okay. So
Okay.
look at the situation. So if I choose a point here, and if you choose a point inside, so let's call this point as 1, 2, 3. Then at point 1, the field will be due to which charge?
So at point 1, negative and the positive charge that is placed at the center
Correct.
of the cavity.
At point 1, the field is only due to the charge in the cavity and the induced charge on the
Yes.
inner side of cavity. So you can answer a variety of problem or a question here. So let E1 be the electric field of charge kept inside cavity. E2 is electric field of charge on inner surface of cavity and let's say E3 is the electric field of charge on outer surface of conductor. So these are three possible electric fields. So if I talk about at point one, so at point one, if you look carefully, the one is the point within the cavity. And what I'm saying is at point one, in fact, the E3 will have no role to play. So at point one, E1 will be the not E1 like E net will be the E1 plus E2. Understood?
Yes.
The net will go to the charge and the induction, the induced charge. Is it clear what I'm saying? So at point one, the E1 and E2 will create the net field. Clear?
Okay. Yes, sir.
Now the most important part is at point two. If you look carefully at point two, two is within the bulk and outer surface. The rule is simple. The outer surface always creates the field outer in outside the conductor only. So the E3 cannot have any effect in the two part. Okay. And we can also see the 1 and 2, the electric field of the plus charge and the induction, they begin and terminate in a small cavity itself. So at 2, the sum of E1 plus E2 will be 0. At 2, if you try to calculate E1 plus E2, so their world will terminate on the cavity surface only. So beyond the cavity surface, they don't have any effect. The first, the third charge cannot create the field within the cavity. At 2, the 1 and 2 will always cancel each other, and E3 is anyway absent. Therefore, the sum of 3 will be also 0. See, isn't it?
Yes, sir.
So at 2, because the net field is 0, so sum of everything is definitely 0. But apart from that, we should remember that the sum of 1 and 2 is also 0.
Okay.
But if I ask you, can we say that E2 plus E3 is 0?
Sir, no, sir.
This is not possible. And now comes the third part. At point 3, the moment you go outside, only the E3 will matter. Rest 1 and 2 is anyway cancelled. So 1 plus 2 together will create no effect because they will not create effect even beyond the cavity. You can see clearly 1 and 2 will end till here only, till surface only. So
Yes.
beyond the surface, 1 and 2 together will have no effect. 1 will have effect, 2 will have effect. The sum will be 0 always. But the E3 will be non-zero. So definitely at 3, the 3 will have the effect. So at any point here, the electric field due to this charge is actually present. You can see, right? So the net field at 3 will be how much? It itself is equal to 3. So the sum, these two is 0.
Yes.
So the net field in the third region will be the E3 itself. Okay.
Okay.
This is what we have to keep in mind, that the net field will be 0. So we can do a very nice problem. So imagine we have a conductor. So we have conductor, and create some random cavity. So the cavity you can see, this is the cavity, and a charge is kept here. That's called Q, and the charge is here. The radius of this spherical conductor is R, and the distance between the center to this charge is, that's called D. Question is, find force on charge that is the question. Find force on charge. What we can see?
Sir, without considering the plus q charge, I mean the plus small q charge, if we consider only the charge inside the cavity like that, we first check the charge distribution, sir, and then we don't consider the cavity charge and we consider the one outside and we consider the charge distribution and calculate the net this thing, sir.
Yeah. So whole idea is because you're looking for the force, so it's good to find the electric field at that location without that charge. So remove the plus small q. Think about what is the electric field present there. So we can say, if you remember the previous question, can I say the force is nothing but the q multiplied by E3?
Yes, sir.
Because what will matter is the net field, and the net field is only E3. And finding the E3 is very easy. Now you can ask why. Why it is very easy?
Why, sir?
Because the conductor is spherical. So for every spherical charge, we know how to think, how to solve. So the plus q will create a minus q here,
Yes, sir.
but it will create plus q on the outer surface. No? And this plus q will distribute spherically due to the repulsion. Because the surface is spherical, so the inner surface will be the non-uniform distribution, but the outer surface will have which kind of distribution?
A uniform distribution.
Uniform. So actually, the charge plus a small q will interact with the electric field of which charge? The charge on the surface, right?
Yes, sir.
So the cavity charge and the plus q charge really doesn't matter in the cavity. So what we are only interested in finding the electric field of the outermost surface, and we know from the concept of electric field. So any spherical charge, what is the field outside? AQ by R square, right?
Yes, sir.
And R we measure from where? The center.
Yes, sir.
So the point P, if the charge is Q, the electric field will be how much? AQ by R square. That's a simple formula we know.
Yes, sir.
And that is the field which will matter. No? Other see the field of plus Q in the cavity and minus induction, they will manage their field within the volume. So they will start and end their own. So the outer world is not aware of the inner distribution. So the charge plus Q will only know the field of this charge, the spherical charge. Understood?
Yes, sir.
So force will be equal to how much?
Sir, KQQ by D square.
Exactly. We can see it's very simple problem, but it may confusing. It may be confusing at the very beginning. So the outer will play the role, and inner will uh, begin and end their field lines. So always remember the force will be due to the field lines arriving at that location, and force is always due to the net field lines. And the net field lines coming there is the charge on the outer surface, so that is what will matter. Other charge should not affect your item. Okay.
Okay, sir.
So if I ask you something, what I can ask. So you can solve many questions from here. This is a very famous question again. Let's say we have a conductor which is spherical and the cavity is also spherical. The cavity can be anywhere, it can be here also, concentric, somewhere here, somewhere here. Now, if the cavity becomes really large,
It becomes a ring.
then this becomes the hollow
So
shell.
sphere. Yes,
Yeah,
sir.
this becomes a spherical shell, right?
Yes, sir.
So we can also think the spherical shell as the conductor with a large cavity. Understood?
Yes, sir.
So imagine if I bring some random charge here. So it will create the electric field lines. It will be like non-uniform because it is not placed at right angle. So you can see the field lines will be like this. It will terminate at right angle
Yes, sir.
as per the theory. If you remember.
Yes, sir.
But if the plus will create the minus here on the inner surface, and you can see the inner surface minus is uniform or non-uniform. The answer is non-uniform. Okay. So what about the outer surface?
So outer surface uniform.
So outer surface is not influenced by the inner distribution.
Yes, sir.
And that is why even if I put some, let's say minus q here, and if the distance of this charge from the center is d here, the force experienced by the minus q will be how much?
Sir, K into capital Q by R, then small q R square. Sorry, D square.
Yeah, so it's the same question.
Yes.
Understood? So that is the whole idea, whether you put the charge symmetrically or not. So similarly, the the electric field lines due to the outer surface will be radially outward because they are symmetrical. So they will create a spherical field. Understood?
Yes, sir.
Clear or confusion?
Sir, now I'm clear, sir.
Great. So they will always ask you the question on the field lines, or you need to identify which one is the correct. So you have to keep all these ideas into the picture, into the mind, so that you can answer the conceptual question. And the most important thing is the electric field lines represent the net field. Okay.
Yes, sir. So,
Hmm.
sir, so why are the electrons like non-uniformly distributed around plus Q?
So the electric field will be stronger near the close to the plus Q charge, right?
Yes, sir.
So the more electron will come there,
Okay, sir.
and on the left side, less electron will come there because you are far away. So your strength is not the same, right?
Yes, sir.
But the outer surface will have no influence because the kind of influence the plus Q is creating is uh, terminated by the induction, the inner surface charge.
Because its net magnitude is equal to that of plus Q.
Yeah. So now the outer induction is not influenced by what is kept inside. So that is like a free charge. I mean, they are free to move on the surface. So they are not like bounded by some other charge. Okay.
Okay, sir.
So they are of course bounded to the surface, but they are bounded means they cannot leave the surface in that way. They are like free to move over the surface, or you can think like the electron will distribute on the outer surface in such a way that the even distribution will lead to the spherical plus charge distribution. So the deficiency will be evenly distributed. That's the whole idea.
Okay, sir.
So what you need to remember is that when the plus and minus are facing, so they begin and they terminate, and the influence of the two will be null outside. So what happens in the cavity will not affect the event happening beyond the cavity. That's simple. Yeah.
Okay, sir. Yes, sir. Sir,
Yes.
uh, the electrons, it will be like, sir, like when they get distributed, a larger charge should be there on a distance like far away from the farther away from the plus Q charge, right, sir? So that like in the opposite direction, if there is lesser charge, only then on both the directions it will like. Sorry, I don't understand like the distribution
Yeah.
part.
So that means that this is our decision. So the electric field is stronger at this point.
Yes, sir.
So more charge will come from the outer boundary towards the charge. So we have more charge here, more aquarium. You can say densely populated. So the population in native charge will decrease as you go up.
So why does it decrease?
Because the electric will become weaker, na? The distance KQ by R square.
Yes, sir.
So the stronger field means
More charge it will attract.
more induction, and the weak film is isn't it? Yeah.
Oh,
So what you can see is the induction process.
yes, sir.
Understood?
Yes, sir.
But this particular influence will not be present on the outer surface. So outer surface will distribute uniformly. Okay.
Okay, sir. Yes, sir.
So now this is the fourth equation. They may ask you a question like this. There's a very fun, nice question I can solve. You have the electrostatic sheet which I have shared. You have.
Yes, sir.
So open this sheet.
Sir, I opened the sheet.
Okay, I'm just opening this. So you can come down. Give me the page number. Yeah, page number 30. So can you see the question number 18?
Yes, sir. So a
Solve.
point charged Q with an electrically neutral conducting shell.
So try to solve this question. It's easy, just think about it.
Okay. Sir, A and C.
Okay.
And sir, the D, due to the charge induced on the surface of the conductor, meaning the
Outer, outer.
outer. Sir, that means the
No, no,
C and D are pretty much the
charge.
same, sir.
Due to the charge induced on the surface of conductor. Yeah,
They
outer.
are, okay, so they are not meaning the inner surface, the cavity, sir. So that means C and D option are both like the same. They mean the same thing.
No, no, the The D option means both surface, inner and outer. The inner cavity, the inner surface of cavity, and the outer surface, including those two. What is the answer?
Oh, sir, only the surface they are talking about. But
Yeah,
then but like the influence on point P due to the system of the small q and the surface charges is 0.
correct.
So here it won't be kq by r square, since they're not talking about the q charge which is in the cavity too.
Correct.
So only A and C.
Correct. Let me just check the answer. I think that should be right answer. 18, 81, part 3, question 18, exercise 2. I think they have given answer B and C. Can you check again?
Oh. Sir, in the A, they're talking about only the charge induced on the inner surface of the conductor, not like the system of the charge and the.
Yeah, right.
So that means it will be B.
Okay.
Oh, wait.
Just take the question. Oh, this is
So why R dash?
let me check. So the first part is due to charge induced on the inner surface of conductor is 0. That's wrong. So at P, the inner surface will have the influence. The sum of inner surface and the charge in the cavity will have 0 answer, right?
Yes, sir.
So A part is wrong. A is wrong, correct?
Yes, sir.
Now due to the charge induced on the inner surface of conductor. So we know that the answer between the inner surface and the charge Q, the sum will be 0.
Yes, sir.
Now, because the sum is 0, so we can find the electric field of the charge due to Q. How much? KQ by R dash square.
Yes, sir.
So that is the answer, no? Because the sum is 0, so it means they are equal in value.
Yes, sir.
So B is the right answer. No?
Okay.
Due to charge induced on the outer surface of conductor. So outer will require R. That's simple. Because for outer surface we take distance from the center. Okay.
Yes, sir.
So that's the answer.
Okay, sir.
Understood?
Yes, sir.
So now you can. So what else you can do is just go below and go to exercise 3. And you can clearly see the question number 18. Can you see question 18? Page number 36.
Oh, okay, sir.
Page 36, question number 18.
Yes, sir.
Know the answer. Come down. Then question number 24. 18, 24. Okay, you can solve these two questions right.
Okay, sir. Sir, mod Q1 is greater than mod Q2.
Right. So we have discussed.
Yes, sir. Sir, J has multiple option.
Yeah.
Okay, sir. Sir, I mean this advanced question, sir.
Yeah.
Sir, that means D option also, sir.
Fine. Yeah. So that's the right of the small q, right? The field is
Yes.
zero. And for 24, that's the main question.
24, it's talking about Gauss law.
No, a long cylindrical shell. Page number 43.
Oh, 43.
24. First question.
Yes, sir. Long cylindrical shell. Sir, in the diagram, they haven't given about like the reason why the shell is having like I mean it has been like half positive and half negative, sir.
Yeah, that is
The
not the
charge.
charge. The idea is like if that is the charge, then which of the following is the most suitable like the first possible? I mean, you have to just reject the wrong one. This is purely logical question. You have to just think logically with it.
Okay, sir. Sir, so
Yeah, then
on this question's answer depend on like to whom the charges are bounded to. Like if the negative charge is bounded to an external charge, then it will be like as if like the field lines are coming from that external charge to this negative.
you
Or
can
if
think,
it is bounded to the other side,
you can
yes, sir.
think this way. Let's say we have uh, two half cylinder. Okay. The first half will have the positive, second half will have negative. And then what I do is I glued them together,
So
making
then
making sure that
first
the
one, sir.
yeah, first is the right answer. Correct. The first is the right answer.
Okay, sir.
And the reason is why? Why it is first right answer?
So when you say it in such a manner, then like when the field lines will come from like the positive to the
Yeah.
negative.
and they will leave the surface at right angle.
Yes, sir.
They will hit the right angle. But the more one more thing that we have to be very careful on the axis, on the horizontal axis, the field lines will be in which direction? Can you guess?
So downward.
Deck.
Oh, so
Or upward. Or upward. Yeah.
uh,
It will not. It will downward only down. So on the horizontal axis, the net field is always downward. Correct.
yes, sir.
Now in any other case, it is not showing.
Yes, sir.
So the only answer is
Okay.
A first.
Yes.
So there are many questions
So
of
why not the second option, sir? Again.
yeah. So now the electric field should be tangential to the electric field line. The net field is tangent to the field line. So if you can you do the tangent at this point, and at this point, how is the direction of rotation? I mean, that second one is very bad. That's the radial. That's wrong. It is starting from here and it is starting from here. Is it possible? So this is plus, minus. Think of a point P here and think of any random plus point here and the equivalent minus here. So the plus will try to create the field like this,
Yes, sir.
the minus will like this.
So equivalently downwards.
So the net field is downward like this. So the field lines must be tangent to here. Tangent.
Yes, sir.
Now that is not possible. To go other lines. Only one is giving the right answer. Correct?
Yes, sir.
So this is the lines of force. So now we can go to the really important concept as well. Method of images. Method of images. So what is the method of images? In case of conductor, we employ the method of images. So So first of all, we talk about a plane surface, plane metallic conductor. So we take a plane. This is the plane metallic conductor. It's basically three-dimensional. So two-dimensional like this. It's a sheet, and what I'm showing you is only the side view or the front view. Okay, so this is the sheet. So we have a metallic plane. It's the plane. So we call it conducting plane. What do you say? Conducting plane. All right. So
Yes,
now
sir.
imagine we have a charge here. And if the plane is really infinite or really big, so how the electric field lines will look like? So one field will terminate from here to here. So plus will come, minus will terminate, and we know that the electric field lines must be at right angle to the conductor, right?
Yes, sir.
And also because this is the nearest charge to the field density, the charge density will be highest here. But as you go away, the density will decrease. So charge will become farther and farther and farther, something like that. So the electric field lines we can draw is but no matter what how they come, they will always terminate at the right time. So you can clearly see that because of the induction process, all the charge coming out of a positive will terminate on the surface of conductor, and also as you go away, it will become rarefied. So you can see the more compact field lines near the below the conductor, and as you go away, so the surface charge density will be uniform or non-uniform.
So it will be non-uniform.
Correct. So the surface charge density will be non-uniform. So that's the first rule is the surface charge density will be non-uniform. So as a result of this non-uniform charge density on the one side, the other side will be having positive or negative charge. Sorry, the other side will have the uniform or non-uniform charge. Hello?
Hello, sir. So are you able to hear me?
Yes, yes. Now I can. So
So
the other,
uniform charge, so uniform densities.
correct. But the infinite plane will make the density almost tending to zero. So can we say the outer surface will have almost no charge appearing? It's so is scattered
Sir, why, sir?
because the charge is finite and plane is infinite. So the sigma is charge upon area. Area is infinity, so this will become zero.
Yes, sir.
So you will get a very weak field. So it is as good as considering. Let's consider no field.
Yes, sir.
Now you can see the plus charge and the minus, which is in the induced here. If I say the height is small h, so there must be some attraction between them.
Yes, sir.
So the question is how to find the attraction between the conductor and the charge. So to find the force of attraction between find the force of attraction between and induced charge, we can use the method of images. So what it says that you can replace the you can think the infinite sheet as the plane mirror. So imagine, okay, what if I ground it here? So if I ground it here, then it is having zero potential. So the potential of the conductor becomes zero. Okay. So the whole idea is this is like a now you can think plane as a mirror, and the plus q will create the mirror image at a distance exactly h below. The rule is can always consider a similar charge at a distance h below, but with opposite polarity. So this is called the image charge, and the plane will act as this plane will act as mirror.
Yes.
So if the plane will act as mirror, then we can have this answer, and the force between them is as good as force between the plus q and minus q at a separation of 2h. That's it. So the force that you will calculate between these two charges will be the force between the conductor and the actual charge. And the answer is pretty simple. Kq square by how much?
H whole square.
So the answer is easy to remember. Kq square by. So this is the force between the positive q and the plane. Because of the charge distribution, it is very complex, but by using the method of images, we can do this. It is clear?
How do we understand?
Pardon?
So why? I mean, like, why will this method work? So, like,
Yeah, so that's a good question why it works. So the idea is, if I take any point P of the conductor, the positive charge will have, so this is the idea which will be more clear after the learning potential. So the potential of the charge will be positive here, and this charge will be negative.
yes,
And
sir.
because of symmetricity, the net potential is how much? 0.
Yes, sir.
So such arrangement will create the same potential distribution as before. See, because I'm assuming the sheet to be grounded, so you choose any point, the potential will be 0 because of this particular arrangement.
Okay, sir.
So this arrangement can be redesigned using the method of images. Okay.
Yes, sir.
So imagine if I give you a question. So now we have two perpendicular conducting plane, and these are semi-infinite. So this is going to be, and now let's say at 45 degree and at a distance r, we have a charge plus B. So now the induction will happen on these two surfaces. So the way of solving is simple. You have to think this as a mirror, and if you know the, okay, because I haven't taught you the geometrical optics, but from the mirror concept, or if we have two mirrors at the right angle, it will create three images. So one will be, and all images will be on the circle of radius r. So that's the whole idea. So for two inclined mirrors, the images will be on the circle of radius r, and the point of intersection of mirror will act the center. That's simple. Understood? So imagine this is the center. Just imagine this is the center. Draw a circle and take the reflection on the surface. On the surface. So one will be here.
Yes, sir.
One will be here. and other will be exactly behind. So it will be like intersection of this. So don't worry if you don't mention much, because this will study in the chapter of optics. So the way to think is the plus will create a minus q here, and this plus will create a minus q. So the mirror image we can assume like this, and the diagonally opposite will be plus q again. That's very interesting image. So why it is happening again? It is happening because the first mirror, let's say this is the first mirror. So the first mirror will form the image here. Is this clear? And the second image will form the second mirror will form the image here. So far clear?
Yes, sir.
Now think of these two as an object. So this object is in front of which mirror? First or second?
First.
Very good. So it will form the image exactly behind here.
Yes, sir.
And this object is in front of which mirror?
Second.
So it will form the image here. So you can see the two images will coincide.
Yes, sir.
And because this charge is minus, so we will take the mirror image as positive. Understand?
Okay, sir.
So earlier we were taking the image of this charge, so we took negative here. But now we are taking the image of this charge. This is positive. We reverse the sign.
Okay, sir.
So actually we have four images. Actually we have
Four images, but one is overlapping.
one is overlapping. So now we have a question. Now this question is like a rectangle. It's like a square because it's 45. In case of rectangle, if I give you four charges, and the diagonal will be how much? So it's a square problem. Correct?
Yes, sir.
And if the question is, can you find the net force on this charge?
Yes, sir.
That's easy to solve. So we can convert this into a problem like this, and we can simply solve the simple Coulomb's problem. So like find the net force. So what will be the net force of this charge?
Sir, KQ square by R square into 1 by 4 plus 1 by root 2, sir.
Yeah, let me check. Attraction, repulsion, right?
All right.
So
Minus
yeah.
1 by root 2.
So KQ square by let's call it A as of now. We can substitute it. So KQ will square by A square attraction into root 2 times cos 45. And the repulsion will be KQ square by and we can find the AF
root 2R.
root 2R. Yeah, towards and yeah. You can substitute here. So to so you can take common as k q square by r square. To be left with is 1 by root 2 minus 1. So you can see we can solve a question like this. Image problem. The image problems are not part of JEE Advanced. It is only part of Olympiad examinations. If you are interested in writing Olympiad, then you should spend some time thinking about this. Else, you can totally leave this image problem. So I think, but in class 12th, you should write phase Olympiad. Are you interested?
Sir, for writing Olympiad?
Yeah, physics Olympiad.
Yes, sir.
So in your school, I mean, they will tell you when to apply and all. So you should participate if it is organized or supported by the school also.
Sir, in Oman, only SOF Olympiads are there, sir.
Oh.
Sir, but I think like IOQM and those kind of Olympiads you're talking about, right, sir?
Right.
Sir, those are like around the same time as JEE, right, sir?
No, it will be
like Jan, Feb.
Yeah, it will be in the month of December, November actually.
November.
Now the schedule has changed. I don't know how they are doing now. So the last year Olympiad got conducted just last month.
Yes, sir.
The month of March. So in the March they finally made this, and because it's going late, so it will be again late in the 12th also. But there is some process of enrollment. You can keep on searching the website, the Homi Bhava website. It happens through the school only, so you have to go to the website Homi Bhava. Okay, I'll share the link. I'll share all the link. The best will be like you can ask Amit Upadhyay sir. He will guide you how to apply and do.
Okay, sir.
So just get in touch with him and ask him about all the details. So he will explain you how to do this.
Yes, sir.
The next part is so the next part I'll cover after teaching you the concept of potential, because right now we haven't studied, so we should leave this part again. So we are done with the electric field lines and how to apply it, how to draw it. So the next part of this theory is called flux of electric.
Sir, can you just come back in a minute?
Right.
answer?
Yeah,
Yes, sir.
just. So now we'll try to understand the flux here. So before we study the flux, let's get some intuition or the intuitive idea of flux. So the concept of flux is always related to some surface or some boundary. So when something crosses a boundary, it generates flux. So in general, if I just call flux, not a particularly electric field, flux is a concept, and it can be due to any sort of field, need not to be electric. It could be gravitational, it could be magnetic, it could be some unknown field like velocity field. So flux is a very generic concept. So we'll try to understand the generic concept of flux, and we'll try to apply it for other fields. So if I talk about flux, then we say it is flow of something across a imaginary boundary or surface. So flow of something across a imaginary boundary surface is called flux. So if we talk about the electric field, then the flux becomes electric flux. If you talk about the gravitational field, then flux becomes gravitational flux. And so magnetic flux, we have velocity flux, we have current flux, and so on. So there are many flux in physics. But to understand or to get the intuition, imagine we have a so we have a shower with many holes. So generally, how the water will come out? So what will come out as a like sprinkling water, like a rain.
Yes.
And of course, gravity will like bend it. So this is the water coming. You can imagine as a some sort of electric field lines or some field lines. And what I bring is some. Let's say we bring a mug. So I'm taking a mug, or you can think it's cup or whatever, and I'm keeping like this. Then I'm keeping a mug something like this. Then I'm keeping a mug like this. If I ask you in which case the water will enter the cup in the at highest rate, one,
Sir, the two.
correct. So you can see that the open surface, or you can see the entry point. So you can imagine this is a surface, And the electric field, you can think of the water flow as the field, electric field. You can see the electric field is normal to the surface, isn't it?
Yes.
But here, electric field is not normal to the surface. And in fact, here, the field is in fact parallel to the surface. So when the field is parallel to the surface, are we getting any flux through it?
No, sir.
So we recently learned about the area vector.
Yes, sir.
So if I take the opening as the surface, imaginary boundary or surface, area vector will be like this. I take like
Yes,
this.
sir.
I take like this. So area vector is always perpendicular. So you can think area vector as electric field. Sorry. So area vector. And you can clearly see the electric field in each case. So you can see that the flux is maximum when the electric field is parallel to the area vector.
Yes, sir.
So at theta equals to 0, flux is maximum. And at theta equals to 90 degree, flux is 0, isn't it?
Yes.
And at theta equals to theta, it is having some value. So which trigonometric function will behave this way? At 0 maximum, at 90 0.
Sir, I don't understand the question.
Which trigonometric function will have
Oh,
0 value at 90 degree and
oh,
90
as an cos, sir.
Very. So in fact, the definition of electric flux due to uniform electric field, the given cross section is given by the field dot d. Ah, yeah, so the flux is nothing but the measurement of E with dot product with area vector, and this is true for uniform electric. And so you can also write as EA cos theta, where theta is the angle between theta is angle between E vector and A vector. Okay.
Yes.
Now it is not necessary that the field will be always uniform. Correct?
Yes, sir.
So for non-uniform field, let's say for example, if you have a surface and if I take a small patch, the area vector will be like this. And let's say the electric field near the patch is in this direction. And the angle between them is theta. So the field will have two components, one E cos theta, another E sin theta. So you can see by common sense that which component will pass through the surface.
So equals theta.
So flux is something which can pass through, not something which is parallel. So something should cross it. And therefore the flux of electric field we can write as E cos theta. So the field which can pass through multiplied by area. Understood?
Yes.
The flux we can write as E cos theta into area, and this we can rewrite in vector notation as E dot D. Understood? And so the flux in general, whether the field is uniform or non-uniform, this way of writing is always true. Now, this particular way of writing, in case of point charge, becomes really interesting. So, imagine if you have a point charge Q, and if you just relate these two like this, because I'm saying this is the direction of electric field, so we can extend this line. Imagine we have a point charge here at a distance r, then this will have the electric field like this only, the way I have drawn, correct?
Yes.
And we can also draw this to the end of the surface to get the concept of solid angle, if you remember.
Yes.
So this is the, let's say, d omega, the small solid angle. So let's do it for the point charge. So for point charge, the flux we can write as E dA cos theta, but the electric field we can write as kq by r square, isn't it?
Yes.
So you can take kq outside. What we left with is dA cos theta by r square.
Yes, sir. Which is d o. So d omega.
D omega, and therefore the answer is kq omega. So for a point charge, the flux you need not to calculate this. We can calculate the flux in only in terms of solid angle. Okay,
Yes, sir.
and the answer is q by 4 pi epsilon naught into omega, which is same as the total flux is q by epsilon naught. So if you remember, the total number of field lines which comes out of charge is q by epsilon naught,
Yes, sir.
and how much it will pass to the surface depends on what is the fraction of solid angle is going through that surface.
Yes, sir.
So this is the method that we employ for the point charge question. So no need to solve by integrating electric. You just do it by think of solid angle. Okay.
Okay, sir.
This is very, very, very important formula. You must remember this.
Yes,
All
sir.
right. So let's do some problem of point charge. Then we'll go for the general question. So we'll do the calculation. So simple question. So let's say we have a surface like a ring or disc, and these are imaginary surface. So there is no physical something physically kept there, just surface. And this surface I'm calling the radius as r. And from the distance x away from this, we have a point charge. So the question is, how much flux will pass through this surface? So we can clearly see that anything within this angle will pass, rest will not pass, right?
Yes.
So everything in this angle will pass through the surface, the rest will not pass, they will leave it. So you know the formula. How to find the answer?
Sir, using the solid angle formula, it is q by epsilon naught into the fraction of the solid angle, that is omega by 4 pi. And for omega, we will be using the formula 2 pi 1 minus cos theta.
Excellent. The theta is here, so you know the formula, so you can substitute, and the answer is simple. Okay.
Yes, sir.
Okay, so what we'll do a lot of question now. We have done with the theory part. So the next lecture will be all about flux and its various calculation and various types of problem. So tomorrow you have lecture in the evening. Okay.
Yes, sir.
So tomorrow I'll try to keep lecture maybe around 7 or 8, because tomorrow is some again function. So I have come to some other city for attending some function. So just in case if I am busy for some reason, I'll just schedule it later, but the class will be there. Okay.
Okay, sir.
So again, we'll meet tomorrow in the evening.
Yes,
Goodbye.
sir. Bye, sir. Thank you, sir.